thought, but the time wasn't enough.
Oreo frappuccino?
Chocolate frappuccino.
I'm gonna watch, even though I don't like both teams, I watch the match just to make sure.
I'm sure it's just as good for you.
Okay. I choose you over Roland.
Not everybody.
That's what Dean didn't mean.
Roland, give it some.
No.
Not.
He is.
Even it's one hand.
No.
Those guys are smart. They know what I like to hear.
The two is different.
No.
The truth? You don't know the truth. What do you know?
But I'm the girl.
So?
So?
So
You thought all of us were ugly,
I'm all
and then your mother said we're all handsome.
Did you just
Is that your story?
Yes.
Awesome. But how did your mother know this?
Her mother.
Yeah, how? She saw you?
Yeah.
Photo?
Yes.
Hold
Ask her mother.
Does your mother wear glasses?
Mr. Steven looks better
yeah.
than Roland.
Your mother wears glasses. Interesting. That is interesting.
What's wrong?
She wears glasses. And when she looked at the photo of this class, was she wearing her glasses?
Yeah.
Are you sure?
Yeah.
Okay.
Steven,
Interesting.
for sure you're going to give us our grades during the test.
Oh. That's why you should have waited until Friday and got them.
Yeah, for sure, yeah.
We'll see.
You see, in life, every person wants something.
Yeah?
I want my math grade, and I suppose...
Are they sour? Deal. What lesson are we on? Materials, isn't it? Do we have homework to do? We have one question.
No, we
don't have this.
Are you sure?
call question and then we
Okay. Next lesson then is this one, is it? We're on to number 5. Our last lesson was ideal gas laws? Yeah, okay. Oh, I'm so sick. Oh yeah, tomorrow. I think we have class at 10 or something, or at 9 or when? 9. At 10 o'clock, I know this sounds like something I'm making up, but it is true, okay? Someone from the head office of DIFC is going to come to the class and film the class. So, if you would like, you know, to come dressed as Goku or whatever,
You would like to bribe us.
yes. And maybe we could arrange some smart questions to ask during the filming. You know, yeah.
What the answers given already?
Yes. I said, Faisal, what do you think about this? Well, I think. Yes. Yes.
According to my speculation.
Yes. So the only reason I'm telling you this is because, you know, I feel like I should, in case they're like, nah, I'll just go to class in my pajamas tomorrow.
Are we the only class that don't?
But then what would happen if...
I don't know. And I don't even know if they're coming to film you, or me, or both. And I don't even know what it's for. I have a feeling it's for a YouTube video advertisement or something like this. I don't know.
So pajamas?
Pajama day tomorrow? Pajama day tomorrow. That's if you're being filmed. Or maybe your faces will be blurred in the video.
I do not see that.
Here at DIFC, we have rehabilitate prisoners.
It's funny, because this place was a prison before, right?
That's true, yes. And then we can have like interviews with people, but they're in the shadows so you can't see them, you know.
Change their voices.
Change their voices.
Oh,
I hear some, could have like fake names like Jack, as he would like to be called. Came from Egypt. Studied on engineering program. Okay.
You graduated high school with a drama degree.
Yes. serve 3 years in prison.
26 lives and 33 seconds.
That's it. All right, next topic now, thermodynamics. Did we miss maths and physics yesterday, or just maths? Well, not really, because you did the topic.
Yeah.
He's good, but his
Too good.
No, he's smart. He's smart. He's teaching them something.
Yeah.
teaching is unexperienced. That's what I thought.
How polite
Mark
you.
probably understood. She
Ah,
was a lot of questions.
No, was she really?
A lot.
Yeah.
For the
Really?
sake of having a communication with him.
Interesting. She doesn't ask me a lot of questions. How many questions?
Like,
A lot.
Uncountable.
to a point where me and Bill looked at her and like, stop.
Wait, hang on a
She lost
second.
her voice even. She was so happy, and then she lost her voice.
Faisal asks me a lot of questions. Your secret's safe with us. Okay, thermodynamics though.
You want to think it's there? I'm away tonight.
What happens in physics stays in physics. Okay. So if you look... Oh no, we'll beat the names out. Okay, so if you look at the word thermodynamics, what do you think it means if you break it down? So thermodynamics. So thermo refers to heat, and dynamics movement. So thermodynamics. You guys are smart. So thermodynamics, more precisely, is a part of physics that studies the movement of heat between different objects. Thermodynamics also studies or is concerned with the change in pressure and volume of objects, not just heat. And statistics is often used. So really the definition is really captured in the first sentence. Thermodynamics is useful because it helps us how to understand the world of the very small connect to the large scale we see every day. And we kind of saw that a little bit last time, where we had a formula that relates the energies of the molecules with... Yeah? Okay. Continue? Just the first sentence.
Conduction and radiation.
We don't study that.
You should hear that. We found one that you would explain to her.
What?
Tell people that you worked with her. The
Is it
Chinese
dirty?
word.
Oh, the Chinese.
Not the
The
Chinese
the
word.
Chinese word.
What is it?
Tell
What?
the Chinese word.
Yeah, little brother.
Yeah, your little brother.
What word?
Tell him.
No.
Say it louder so he hears it properly.
Say louder.
I heard it. The Chinese word.
Chinese, right?
Chinese word, but it has a meaning in English.
I know that. But they're bad boys and don't listen to them, okay?
You know what was really weird?
What?
She had like 3 other teachers and none of them had a clue what she was talking about.
You think?
Maybe they were just plain stupid.
I believe not.
Really?
Yes.
Which teachers did they ask?
Miss Lorraine, Miss Isabel,
Iman.
and Miss Iman.
No. They were faking, I'm sure. Just convincing. You believed? They're just convincing.
No.
No, Lorraine knew, I think. Dr.
Yeah.
Lorraine. But they
knew for sure.
No, he sounded so serious about it.
David always sounds so serious about things when he's just joking.
Yes. Okay, continuing. Now, we have seen that the kinetic energy of an ideal gas we can get from this formula, you remember. But we also know that PV equals NKT or nRT if you're using moles or molecules.
Okay.
So, K, Boltzmann's constant. Were you in this lesson?
Yeah.
So we can say that 3 over 2 E equals nkt. By dividing we get T equals 3 over 2k E over n. If I just simply, where's it gone? Divide by nk. Now this result is very important. This 3 over 2k is just a constant. And E is the total kinetic energy, and N is the number of molecules. So what do you think E over N is? It's like an average. Total divided by N. So let me just make that a bit clearer. So, and we have PV equals
the energy of
NKT. Getting there, yeah. PV, we also know, equals 3 over 2E. So 3 over 2E equals nkt. So T equals 3 over 2k times E, but just remember E is kinetic energy, and N. And this is the total. But if you divide by N, then it becomes an average kinetic energy. And this is just a constant. So you can get the result that T is proportional to average kinetic energy. And that is a very important result, extremely important result. So I think it would be very good to write this down. So given this, we know this, we did this in the last class, then we can show this. Hardly a proof, it's like 2 lines, so please write it down. Okay, you got that? There's a couple of ways to write average. You can write it like this, average kinetic energy, or sometimes people write it in brackets like this, or sometimes people put a bar on the top. So you have 3 ways to write average. Oh, okay.
What's the exclamation mark for?
Importance. Okay, continue, please. Yes. Okay.
It's a formula.
What?
What is the formula?
No, it's not. Listen to him.
Oh.
So we have this result. Very important result. It's important that the temperature is kinetic energy with just a change in units. The reason this is important, average kinetic energy, it basically says what is temperature. Temperature, except for some units here to do with the constant, temperature is essentially average kinetic energy, which means that as the temperature increases, the average kinetic energy increases. So for example, if you double the temperature, then you double the kinetic energy of the particles. And if you half the temperature, you half it. But this gives us an interpretation for what happens when temperature equals 0 Kelvin. That means the average kinetic energy will equal 0 joules per molecule. So if the molecule has no kinetic energy on average, then its motion is stationary, not moving. So this means that 0 Kelvin corresponds with absolutely zero motion. All the particles are locked into place.
So,
And this is why we can't have negative temperature of Kelvin, because we can't have negative kinetic energy. And the reason we can't have negative kinetic energy is because mass and velocity squared must be positive. Now you were asking me, could it be below it? And this is why I was saying, well, maybe if you had some weird negative mass antimatter, maybe you could. And then what about, could V squared be negative? Again, you could have some particles where the speed squared is negative. It would have imaginary speed. What would that look like?
But that's squared anyway.
Yeah, I squared. It's not something we do. Did you study I squared before?
I saw from it.
Yeah. Anyway, this is really important because it gives a clear interpretation of what kelvins represent. They represent average kinetic energy, whereas 0 Kelvin
question.
corresponds to no motion. Yes?
So does that mean that the particles are stable and absolute zero?
What do you mean by stable? You mean stationary?
Yeah.
Yeah, they're completely stationary.
The electrons do not move inside the particles?
No, we're just looking at the movement of the
vibration?
molecule. Yeah, the vibration.
So
Yeah.
they don't vibrate.
They do not vibrate.
So can we say the colder the object is, the harder it is?
Yeah, technically. Is it frozen?
Yes, because yes, they should be locked into place if they're not vibrating. But I don't know if that really represents harder, because harder's not like, I mean, what do you mean by harder? Do you mean more difficult to break or more solid, or or do you need more force now to break it? You know, so harder's not exactly a precise term. We can certainly say that it's not a gas or a liquid. It can only be a solid at 0 Kelvin, because liquids and gases, the molecules move around, but only a solid can it be locked into place. So I suppose, yeah, I guess you could say it's harder because it has to be a solid. What you might get in the exam is they might say, explain what is meant by an absolute scale, and an absolute scale means a Kelvin scale. So the answer is basically, for an absolute scale like Kelvin, temperature is kinetic energy, which is a change in units. In other words, no temperature means no kinetic energy, which means no movement. So this is what is meant by an absolute scale. In physics, if you use an absolute scale for temperature, it means you're setting it so that 0 on your scale represents 0 kinetic energy and 0 movement and absolute minimum temperature. So you don't have to use Kelvin, you could use some other scale, it's just we use Kelvin. Whatever the absolute scale is, it must start at 0, and this is why it starts at 0. What? Shaking head is good or bad?
Falling asleep, getting sleep.
Long day, huh?
Yeah.
And you're in my class and there's blah blah blah, blah blah blah. And like, yeah, absolute 0. Okay, so for the exam, we definitely want this here. Well, basically the whole paragraph here. This is a very important result, and it gives a reason why an absolute Kelvin scale is so important. So this could be the question. Why is an absolute scale like Kelvin so important? Because. Can you write that down?
We at 273.
Point 15.
What's the value of K?
What do you mean? Oh, Boltzmann's constant. We said it was something like
V over
Avogadro's. The ideal gas law constant over Avogadro's number makes the Boltzmann's constant. Is it nap time, Faisal? Afternoon nap?
Don't get this. Sleep early, wake up late. Late as in 7:30. I eat
Maybe-
healthy food and I still get sleepy at this time. And you know what's really annoying? At night I'm not sleepy.
Yeah.
That's happening.
Maybe you're not used to the hot weather here.
Yes, sure.
It's making you sleepy.
How physics of you.
Why don't why don't we use Celsius instead of Kelvin?
For the reason I've just been talking about for 5 minutes.
Like why don't people use Celsius instead of Kelvin? Like if
Because
that's
if you use
zero,
this in this formula, you won't get zero.
Yeah, but then you go minus the 70.
We don't want minus. We want up.
We don't want minus, we want 0 to be the starting point. Okay. So some definitions. Internal energy of a gas, or liquid or solid, but usually a gas, be it solid, liquid or gas, is the sum of the kinetic and the potential energy. So in other words, yes, you remember this, if you have some gas with lots of molecules in it, the internal energy is you add up all the kinetics and all the potentials of each particle. That's the internal energy. That is, it's the total thermal energy, which is the kinetic and the potential. So as a formula, basically, we have this result. Internal energy is all the energies, which is all the kinetics plus all the potentials. Now this, of course, is a very big number because you have so many molecules in a gas. So you never really calculate this because you can't. You cannot calculate all of these. There's too many of them. But this is the definition of U. But it's only a definition. You cannot really use this formula to do anything. The formula is key here. Although I say formula, it's really more of a definition because you can't actually use the formula in a useful way. Did you study this in A-level physics or something?
Yes.
Yeah.
It's like unit 1, like the real beginning of physics. Yes.
They do this in the beginning.
Yes.
That's lame.
I think so.
I think you're right. I think I remember looking at the book and they have materials at the beginning.
Yes.
Yeah, materials.
No likey.
No likey whatsoever. We did this, we did viscosity, we did elasticity and plastic and elastic and the graph and that and that's in the viscosity formula there's this end that goes all the way down.
Oh, ETA, yeah. Don't worry.
Terminal velocity inside viscous liquids.
We don't have all of that. Okay, continue. You have this?
But it was still interesting.
Yeah.
Yes.
Now, heat is a form of energy and not a physical substance. So heat has no mass. heat can move from one place to another in different ways. In thermodynamics, what?
We asked our teacher when we were doing materials, why are we studying this? And then he gave us a nice example. It's like the Twix you eat. They don't measure the viscosity of the caramel and the chocolate and figure out the right temperature. So not be as tasty as it is right now.
Good enough reason. Heat means energy which is moved between two things when one of them is hotter than the other. Heat is not the same as temperature. So heat is not temperature. Remember, temperature we measure in Kelvin, and Kelvin represents... No. Temperature we measure in Kelvin, and Kelvin represents temperature. Done. No.
Absolutely.
Thank you. Average kinetic energy, okay? But heat represents internal energy, which is a total energy. Do you see the difference? Temperature is a statement about kinetic energy, whereas heat is a statement about average. So earlier in the semester, Faisal was unhappy with me using the word boiling instead of evaporating. So this is what happens. Let's imagine you have a puddle of water on the ground. Here's our water. And what temperature will we put it at? 20. So if we go in Kelvin, let's just say 300 Kelvin. It's warm water, 300 Kelvin, okay? That is a statement about the average energy. So because it's an average, that means some parts will be hotter and some parts will be colder than this. But on average, it's 300. What happens is, up the top here, we actually have some of the water at boiling temperature of 100 Celsius or 373 Kelvin. Now you might be thinking, why can't I feel that? Because when you stick your hand in it, you get like what you might say a sample, which is also an average. You're not feeling the very top, you're feeling an average, which will still feel like 300.
No, but in chemistry it was different, like the reason for this was different.
Go
It
on.
was like that the atoms, some atoms they don't have complete bonds, so they just like shoot off in the air.
What?
Yeah.
They evaporate.
Yeah, they evaporate.
They
The
shoot
bonds
off between.
like they just like
They turn into gas, basically.
yeah, they break and they turn.
Yeah, that makes sense because they are gaining enough energy, heat energy to break the bonds between them and turn into a gas.
Unless you prove this to me visually, I'll never believe it.
Do you ever see something drying, like some, I don't know, like a wet towel or something like this?
Me, when I come out of the shower, I'm steaming.
Okay. But let's just say...
Because it's hot water, but I know it's not 100 degrees, but it's still steaming. So how is it steaming and it's not 100 degrees?
Because the outermost layer is... Yeah, okay. Do you ever see, like, I don't know, a towel on the heater or whatever that's wet,
Yeah.
and if you look closely you might see some
Yes.
steam coming off it?
Yes, yes.
How do you make steam? By boiling water.
Yeah, but...
But what?
Okay, now it's all falls apart.
So anyways, this gives us the difference between temperature and heat. They're not the same thing, okay? So this means the temperature is an average speed. So for example, listen very carefully to this sentence. A swimming pool at 20 Celsius has more heat energy than a cup of coffee at 80.
Because it's bigger.
Yeah, because it's bigger. However, the cup of coffee is hotter because it has a greater temperature. So you have to be very careful with your English here. Unfortunately, when we say hotter, we're not talking about heat, we're talking about temperature.
How English show in science.
Yes, yes. I can see how unhappy you are with that. So just please be very careful with the word hotter. By hotter we mean bigger temperature, not more heat energy. Yes? So please just be careful with that. Heat or thermal energy, some properties. It is something which may be transferred from one body to another. It's measurable, so you can measure it obviously. And it's not a material substance. You can't hold heat.
You can only contain it.
Yes. Because it may be transferred from something which is not a material substance. Heat is a form of energy. Okay, so you can transfer it, you can measure it, it's not a material, and it's an energy, a form of energy. So can you bullet point those 4 properties? It looks like it's nap time for Lee. Continue.
What's the third one?
It can be not treated as a material substance, and meaning that you can't treat heat like it was something of material form. You can't say, I have 1 box of heat.
Because it may be transformed into something that is not a material substance.
Yeah, so basically,
It's energy. So
It's
energy can be
energy,
transferred
yeah.
from
I
one
mean,
form to another.
we think of something which is hot, like the microwave. Inside the microwave, obviously there's heat, but there isn't anything with that heat. It's not like inside the oven where the air inside it gets hot because the back of the oven heats. So, in other words, heat can, many things can hold heat, and those things can be something material, like a table can be hot, or it can be something like electromagnetic wave, like a microwave. So I suppose the point I'm trying to make with heat is it's not really confined to only physical things like, a piece of wood or a piece of plastic. It can actually exist in radiation or many different forms. In other words, heat is something very universal.
Question.
Yes.
If there's a flame
Yes.
and we get close to the flame,
Yes.
are we feeling the heat or are we feeling the hot air around the flame?
Okay.
But you are feeling the heat through the hot air, like the heat from the flame heats up the air, which heats up your hand. So precisely what you were asking.
If it's not,
It would have to be the air, because
yeah.
the heat has to transfer to you through some medium. So it has to be the air.
Like if we're in outer space
You wouldn't feel the heat.
and we're close to the sun.
No, because the sun is not a fireball.
Fireball.
Please, not Pitbull songs. The sun is not a fireball. It's not a ball of burning candle.
It makes radiation.
Yeah.
So will we feel the radiations or will we feel our skin getting hot from the radiations?
Oh, I see what you mean. Yeah. No, it'd be your skin slowly cooking that you would feel. Yeah, it's nice and crispy. Bit of orange sauce, Okay. Yes.
Is the top layer, like let's say of this table, more than 100 degrees?
It's not evaporating.
No, but then, I know.
No, sorry. I'm going to stop that there. Faisal's answer is the best. The table is not evaporating. It won't slowly turn into gas. So
Water is at 100 because water evaporates at 100.
Yes, but
things which are evaporating, the top layer would have to be at a boiling point.
yes, but then water is at 100, like, and it's in the same room with the same temperature.
Yeah.
And like wood doesn't evaporate, it doesn't boil at like 100 degrees, so
There is a bit more to it than what I said. So obviously, if you spill water on the carpet and spread it out thinly, then that will evaporate much quicker than if you just put the water in a cup. So there is other factors at play, like for example the surface area. So by spreading the water out on a greater surface area, you can speed up the evaporation. And the reason for that, I'm imagining, is because you have a greater thin layer, and the thin layer on the exterior is what evaporating. So if you just have water in a cup, you have a smaller area than if it spills on the floor.
Yeah, but what I'm saying is that like is the top layer of everything in the
No.
same room, the same temperature.
No, it depends on many, many factors. I just know for water, it would be in the room. But I mean, just because it's a liquid, it wouldn't be. Some liquids would evaporate much sooner than water, you know.
Do you
Okay.
know of any swimming pools around?
There's no temperature.
Isn't there one in Rathmines? I don't know.
There's a swimming pool.
There's a website where you can look up things like this called Google. I don't know if you've heard of it,
Oh.
but you can easily check many things like this on Google. Okay. The heat supplied Q
I feel like swimming.
is the energy pumped into the system. Yes, and so I'm put pumped in quotation marks here because pumped we usually use to talk about water. But often people use the word pumped here when they're talking about putting heat into the system. So for example, if you're boiling water, you put the a saucepan of water on a heat source. So you're putting heat into the water. So this heat energy you put into the water, you call it Q. This is the energy you provide, or as we call pumped into the water. So you're literally putting heat energy into the water. And we'd use the letter Q for that. So if you can make note of that definition, please. Can you like nudge him awake or something? Oh, no. Hang in there, Lee. I'll give you a break shortly. I know.
The reason you came in today.
I know. It has nothing to do with me. Okay, do you have this definition? Go on, you have this? Yeah. Okay. For example, a train engine works because it gets heat energy from what?
Charcoal.
Coal, a fuel supply. From the burning of coal. The heat energy is converted into work. Well, I have a picture of this later. Anyways, more definitions, I'm afraid. Two physical systems are in thermal equilibrium if no heat flows between them when they're connected by a path which allows the heat to flow between them. Basically, that's the technical definition, but basically, they're at the same temperature. So this is a fancy way to say they're at the same temperature, but it is the exam definition for it, I'm sorry.
But like, if we have two pieces of metal and they're attached to each other, and they're the same temperature,
Yeah.
there is nothing going between
No,
those two?
there is something going between them, but heat isn't transferring between them. So, for example, maybe some of the, let's take two gases, for example, at the same temperature.
Yeah.
We put them together. I'm not saying there's no exchange taking place. I'm just saying there's no heat exchange taking place. So,
Oh,
if gases swap places, because they mix,
yeah.
it does not affect the heat energy. There's no exchange of heat. It's not like one gas gets hotter while the other one gets colder. That would be cool, but it doesn't happen. So, if two bodies are at the same temperature and no heat flows when they're in contact, we say they're in thermal equilibrium.
What happens if we put really cold gas and really hot gas suddenly together?
You get a warm gas.
That's it? Like if it was really cold surface and really hot water, or the other, really hot surface and really cold water, the water will and you'll hear something, but nothing happens with gases.
It's hard to have a really cold gas because it kind of turns back into a solid liquid. So I don't know.
What's the coldest temperature gases can exist in?
You can kind of make the gas temperature anything you would like as long as you adjust the pressure. So for example, you could have water.
Even if we go to Antarctica, it's -40 and 30, there is still air to breathe. So there is still gas at negative 30,
Yeah.
40.
True.
So why doesn't that gas turn to water?
Because of pressure differences too, I would imagine.
But the pressure of the Antarctica is different from the pressure over here.
I don't think the air is at minus 40 in Antarctica. I'd have to check that though.
If we hold the thermometer in the thin air, I'm pretty sure it will read less than 0.
I know what our next field trip is.
No,
Right.
seriously. I'm just thinking about this. Like, why doesn't that air turn to a liquid or a solid?
Well, the air is oxygen and nitrogen, which doesn't freeze at minus 40. But any moisture in the air, I'm sure, has already frozen. So Antarctica is a very dry place. In fact, it counts as a desert.
Yes, true.
Satisfied now?
That's it.
Right. Here's an example of the point I was making earlier. A very simple engine.
It's,
So what happens here is you burn the coal, and this provides heat energy.
cockshot.
Focus, please.
Old school mechanics.
I'm going to start getting angry at you now. You heat the coal, you burn the coal, provides heat energy, and this heat energy, by using a water steam engine, the heat energy is turned into work. So you can put heat in, and what do you get out? Work. Yeah, kinetic energy, very good. So Q is the heat energy pumped into the engine from the coal being burnt.
This is because the water particles begin to...
Yeah, the water and the steam is not so important. That's just the way you can get the heat energy to do work for you. It's just the sort of the mechanism, if you know what I mean. What I really just care about is what goes in, which is the burning of the coal, and what comes out, which is the moving train. This heat and steam this water and steam is just a way to, get the heat into work.
How can heat into
Pressure.
What happens is when you burn the coal,
yeah,
you make the water hot. The water becomes steam, and the steam pushes a piston.
what happens after
This moves back, and then continues around. Piston pushes
the
forward.
to-
So what happens is this fills up with steam and pushes this back, and then the steam comes out, and then it comes back, and then you fill it up with steam again. So it's like here,
the car.
just like with the car, yeah. So if you look
No,
at the
the car
train,
can-
on the side, you can see the steam coming out, and on the top, do you know, this morning I'm thinking, I still feel a bit sick, but no, I can't miss another day. I just like to say, I'm really glad I came in today. I don't feel like I made the wrong decision at all. Okay.
What does permeable mean?
It allows the heat to transfer. Okay. So Q is the heat energy. U, or delta U, it doesn't matter which, that's the change, well, here it does, the change in internal energy. So question, what is the internal energy here?
The charcoal.
No, because that's the energy provided, so that's the Q. But again, the steam is like the Q because this is the heat you're
The
providing.
temperature of the empty engine.
We're getting closer.
The temperature of the whole train.
Closer, but not quite there. It is to do with the train or the engine, doesn't matter which. So the delta U is the increase in the energy of the train.
So initial minus final.
Or the other way around, yeah.
Final.
Because when the engine is on, the train, not only does it do work, but it also gets hot. And finally, W is the work done. And what is the work done here?
The output.
Yeah, which in this case is kinetic energy. So, what does the conservation of energy state?
Energy can neither be created nor destroyed. Can
Thank
only
you.
be transferred from one form to another.
Beautiful. So here's the engine here. You provide it with heat energy, and then what do you get out in the end? you get kinetic energy. So you get work out at the end. But in the process, what happens to the engine? It heats up. You never have a cold engine, you only have a hot engine. So it gets energy too. Where did this energy come from? Yeah, but where did it come from?
From
The
thing
Q.
you put in, yeah.
And where did the W come from?
From the U.
Well, from the Q.
change in the U and Q.
From the Q. From the Q. This goes in, and this is what you get out, so to speak. In other words, Q equals delta U plus W. Or I think it might sometimes be written as W equals Q minus delta U. Let's see what I went for here. Q equals... No, I kept it like this.
So they ask us, why is there a change in, between the heat energy and the work, like in terms of energy, like where does the energy lost go? We can't say it was wasted as heat energy. We have to say it was wasted as internal energy, or it was changed to.
Internal energy is one form in which the heat was wasted, but also the work done is making kinetic energy, but there is wasted energy as well. So not only do you have your train moving, which you want, but you also have it making sounds. You also have other things happening with the train as well. So I would say actually the most of the energy loss is not true. I mean, the internal energy would be a significant loss of energy. But it's more than just the internal energy, because the train is giving off heat as well. So that is one form of lost energy, is the internal. Okay, continue. Yes, continue, guys. In the last diagram, heat was provided, and the result was increase in internal energy and work. We don't really care about this. What we really want is the work done. However, it is possible to do work and see an increase in heat energy. So think about it. In the last one, we provided heat and we got work. So the question is now, can we provide work and get heat? Huh? Yes, again? If I was Roland, you would say it again. Okay, so shown below is a way to convert work into heat. It's a very old experiment, but it's a really nice experiment. Let me explain it. You hang a weight here, and you let the weight slowly fall. Okay? And this weight is hooked up to a wheel, and this wheel is to another wheel. So what happens is, as the weight falls, this wheel turns like this. And at the bottom, there's two paddles, two boards. So they turn with the wheel. And this is put into water, and here you can see a thermometer. And as this falls, the thermometer increases. So you've changed the work, which in this case is potential energy, into heat. The heat energy has warmed up the water, causing the temperature to go up. This is a very simple, very old experiment. It's the first experiment that shows, that proves you can change work into heat. Before this experiment was done, everybody knew you could change heat into work. Like, for example, if I heat up this door, I can break the door. So I've changed heat into work of breaking the bonds in the door and so on. But the opposite was not clear. Can you change work into heat? And the answer is yes, you can. By the same formula as this one here. Okay, so if you want, you can say work equals heat minus internal energy, or you can also say this one here. Heat is internal energy plus work. In this case, what is the internal energy?
Temperature of the water.
Kinda, but that's kind of like the heat. That's what you wanted at the end. So it's not quite that.
The weight of the mass.
That's not heat.
Yeah.
That's work. That's work.
Between the
But that's not heat.
heat.
Internal
Temperature of
energy.
the water before.
No, that's the Q. That's what you want. The internal energy is the increase in the temperature of the instrument holding it. So not only will the water get warm, but also the container will get warm. And this is the U. Yeah? And the rest of the machine too. Okay, so now that we have all our definitions, we can now talk about 3 laws of thermodynamics. So you know that Newton had 3 laws for mechanics. Now we have 3 laws for thermodynamics. And the first law is not called the first law, it's called the zero law. The reason it's called the zero law is because it's so basic. The zero law states, ready? That if 2 thermodynamic systems are each in thermal equilibrium with a third, then they are in thermal equilibrium with each other. What does that mean? So, for example, if this is the same temperature as this, and this is the same temperature as this, then that means these 2 are the same temperature. I know. And this is why it's called the zero law, because it's...
They made a law
Yeah.
for this.
When it's like eating the opposite.
It is. That's why it's called the zero law. So some people don't actually count it in the 3 laws, but it really is one of the 3
So
laws.
there are 4 or there are 3?
There are 3, 0, 1, 2.
Oh, so, okay. What's 1 and 2?
We're getting there. Do you want to write this down?
No need.
Write something, please.
So you want us to write this down?
Yes.
Did people respect whoever made this law? Like
No.
give them money or anything?
No, like the previous experiment with
When you
the...
make a law, you don't get paid for it.
The previous experiment...
Yeah.
The previous experiment where we showed that you could change work into heat, at the time nobody believed that this was really the case, because at the time, about 120 years ago, people didn't feel like it would be possible to change work into heat. That it doesn't seem to, it was difficult to imagine that you could do that. There are other experiments to show that you can.
I was thinking, the rubber band,
Yes.
if we stretch it, we feel the heat. Is it because of the work?
Yes,
or is
yeah,
it
yeah,
because
yeah. I suppose you could say that you're doing work and you're making heat, although I suppose that's a bit more like friction than...
Yeah, between the bonds and...
And anyways, in thermodynamics, we're usually dealing with gases, so this is the context. Okay, continue.
Do we need to write the law, like if they ask it in the exam, the same way it's written here? And we'll just write it in simple words.
No. You cannot.
Will they even ask it?
Highly unlikely.
Then 2 of them have the same temperature.
Yeah, but you have to use the word thermal equilibrium, then the same temperature. Okay, continue. Law number 1. The first law states, it's basically a version of the conservation of energy. That is delta U equals Q minus W. So in other words, this is often rearranged as this delta U is Q minus W. So the increase in internal energy is equal to the heat supplied minus the work supplied, the work output. So the question is, you were asking me earlier, how can we explain the difference between work and Q? And I was saying a significant part of it is the increase in internal energy. That is the difference between what goes in and what comes out. So it is a type of inefficiency. So basically the same formula again. This is the first law. Continue. It's just the formula you need, okay?
Oh.
Continue.
Yeah.
And thirdly, the second law states that heat cannot spontaneously, that means by itself, flow from cold to hot without some external work being performed. So in other words, heat only travels from hot to cold, unless of course you're doing some work to make it travel the other way, cold to hot. And this, one sec. So for example, if you have something which is hot and something which is cold, then the heat will flow this way. If you have something which is cold and something which is hot, the heat will not flow this way. It doesn't, I mean, this doesn't get hotter and this doesn't get colder. It never happens this way. The only way you can get it to flow the opposite direction is if you do some work to make it flow the opposite direction. And you have some systems for doing that, to make the heat flow from the opposite direction. I'll give you an example of one, but before that, your question?
Yeah.
Is this, okay, an example of this, where you can flow from cold to...
Yeah, cold to hot.
From cold to hot, yeah. Right, so for example, let's say you're in a room here and this is at 20 Celsius, and then you have some, in a box, some food at, I don't know, let's say it's a little bit cooler, let's say it's only at 5 Celsius. So what should happen? The heat from the room should flow into the food, and the food should warm up until it reaches equilibrium, which in this case is 20 Celsius. Now, can you think of a situation where that doesn't happen, where the heat doesn't flow from here to here?
Fridge.
The fridge, yeah. So, let's say you have your fridge set to 5 Celsius, and you put some food in it, and you got the food from the garden. So let's say the food is quite warm. Let's say the food is 20 Celsius. What happens? You might think nothing happens because these are at the same temperature, but the fridge will take heat out of the food and put it back into the room. And then this will decrease to 5 Celsius. And in fact, the room actually gets a little bit hotter, but you don't really notice it. But the next time you go to your fridge, put your hand at the back of the fridge on the ground and you will feel the heat coming out. So the fridge is pumping the heat out. The fridge is doing work. This is the only way to get heat to move from cold to hot. Other examples, air conditioning and other things like this. Radiators? No, radiators.
Don't they keep the things cold?
No. Radiators get hot and this heat goes to the colder room. Do you have some kind of like Middle Eastern radiators that cool the house down, but they work reverse or something?
No, not the house, cars.
Oh, the air conditioning in the car.
No, the radiator in the car. That
Oh!
cools the engine down.
Now, this might be an English thing. I don't know. In Ireland, what's on the wall in a house is called a radiator.
Yeah, I know. Even
Yeah.
in Iraq, we call it the same.
The radiator in the car.
Yeah.
It
It does the exact opposite of the radiator at the house.
takes heat away.
Yeah, it
Yeah.
cools down the engine.
That's probably why.
No.
Yes, it does.
So it does cool it down, but it's not an example of this. Because if you think about the car engine, we'll put the car engine at some hot temperature like 200 Celsius. And outside is 20 Celsius. So the heat will still leave the engine and go from hot to cold. All the radiator is doing is speeding up the process by having some sort of liquid that can take the heat away faster. So it's not quite the same thing. It just tries to speed up the natural process to get the heat out. So you realise then if you take your car to some place really hot, then the engine will completely break, because instead of the heat being taken away, it goes back in.
Yeah, that's the thing I don't understand in our countries, like in Kuwait or Saudi Arabia or something like that. Temperatures rise to like 60, 50 something degrees.
Yeah.
The cars like work better than other countries.
60 is a little bit too much, honestly.
No,
It goes to
Okay, but what do you mean cars run better?
like I don't know if that's a country thing, but in Egypt they have I know they have worse cars,
But the quality of the cars.
The quality of
yeah,
the
but what difference? Like in Egypt, we have less temperatures, but cars work less efficiently. I guess they are worse. I mean,
There's too many factors there. Probably the biggest factor per country is the quality of the petrol. So in a place like America, the petrol is of a lower quality because they add more to the petrol to reduce the cost. Whereas in a place like Saudi Arabia, I imagine you're getting pure 100% oil, quality grade. There's no need to add any.
black gold.
That's
Yeah.
that's
No,
an
they
option.
still cheat.
Shut up, shut up.
Well, they cut like a lot of petrol stations.
They add a little
They
bit
mix,
of
like,
that little bit of water
yeah.
into it, and yeah, save some money.
But no.
I think
There's
that's
another-
probably the biggest factor.
Yeah. You have different types.
Excellent. We have excellent and normal and regular. Excellent
And you have the
petrol and
choice.
regular petrol and diesel. Over here, so many cars uses diesel.
And
In
most
the
expensive.
Middle East, no one uses diesel except the big
Trucks,
truckers,
yeah.
and lorries.
Now,
Yeah, no cars use diesel.
Yeah.
guys,
Yeah, money.
if you do something like mechanical engineering or yeah, now that's do without a hyphen. Okay, so if you do something like mechanical engineering or something to do with automotion at university, you will discuss thermodynamics a lot. Thermodynamics is extremely important for engines, as we've been discussing. Basically, this is the physics of engines, and this is the reason why this topic exists, because about 120-40 years ago, when people first made steam engines and then later petrol engines, really there was a requirement for a branch of physics that studies the behavior of heat and temperature. Okay, so this is really, really important for engines, which makes it still important today, especially as we're talking about more efficiencies and things like this. Do you have these three laws? Not yet. Finally, for these three laws, the second law can be stated in many different ways. This is just the easiest way to state it. You got that, Florence? Continue? Yes? Continue. Right. Oh my goodness. Who's still? Yeah?
The hot can be cold, but the cold has not be hot.
You can, heat will move from the hot to the cold, but heat cannot move from cold to hot, unless you do work to move it. Yeah. This is how a fridge works. It takes heat the other way.
But the thing is, the first is hot and then it comes to cold.
Yes. The fridge. Let's say you get some food from the supermarket. What temperature is it at? 20. Okay. And you listen. You put this food in the fridge and it's at 20. Yeah. What will happen to this? Let's even say the room is at 15. Listen. Let's say the room is at 15. Okay. You would think, okay, this cools down to 15. And this is okay. This is what you think should happen. If you have something hot and something cold, the heat will flow from the hot to the cold. So this is normal. However, it will continue to fall until 5 Celsius. So this means the heat must be flowing the other way. This diagram is ugly.
What?
Let me try and draw this again. Okay. Fridge. Room. 15 Celsius. And food is here at 20 Celsius. Which is hotter?
Fridge.
Yeah, you just put it in the fridge.
Oh.
So which is hotter? What's in the fridge? So we expect the heat to flow this way. This is law number 2. Second law. So then this reaches 15 and this is at 15. So we think there should be no flow. But what will happen now? It will continue to decrease to 5 and this is still 15. Yes? So the heat continues to flow this way, even though we think it should flow to the right. And the only way it can flow the wrong way is because the fridge is doing work. Yes? I know this is a bit complicated, but simply put, heat travels from hot to cold unless you do some work. Let me give you another example. Let's say you have some... can I scroll down? No. Well, I'll zoom out. Here's another example. Here is the North Pole. This is where Santa lives. And here is Ireland. Which is hotter? Ireland. Don't think too hard, it's Ireland. So the heat should flow upwards. But sometimes you see on the weather, you have cold air travelling down. You know, this is the opposite of what you think. Yeah, so the wind is doing the work. The wind is moving the heat in the wrong direction to what you think it should be. Yeah. So if the wind is doing work, then I think that means when it's finished doing the work, the wind should be blowing at a slower speed. You get what I'm saying? Yes? No? I know it is a bit confusing. It is a bit confusing. But no, we're focusing too much on the second part. Most importantly is the first part, that heat cannot flow from cold to hot unless you do work. You make it. I said, wrong, I need to continue. But what I recommend you Google later, in Vietnamese perhaps, something called a heat pump. And a heat pump takes heat from cold to hot. Look this up later. Okay. I'm going to give you 2 questions to do. Then when I come back, we'll do the answers and you'll have your results. Provided that you have these 2 questions done. That's right. If you don't have the answers, I don't give you your mark. If you already have the answers, I'll deduct your marks. I want my sour candy.
We made a deal.
I'm getting the result now. You want the result? Give me sour.
I'm getting the candy out now.
Give me. I need the energy to get to the office. I can't make it. I'm too weak.
Give us the girl and give us the money.
I don't think I can make it to the office. Right.
Sorry, don't.
I'm not going anywhere. Right, I want these 2 done, and then when I come back, I'll have your maths results. Better bring back the right results.
Did he get the physics results?
We had a lesson like that.
I remember the lesson in class, but I don't remember him telling me my mark.
Yeah, you got it before. You and D got it first because you were on the right 78. You remember when we were doing the experiment, you knew your work kind of compound.
Yeah, but I don't remember
Yeah, I
him
know, but-
telling me. No.
Yeah, that's
Oh, yeah, he wrote it
That's
down.
wrong.
People when they came
It depends.
No,
Some car cannot.
Look,
no, some cars can't take these.
If you want
Yeah,
to
yeah.
drink
take petrol.
tea,
Depends on the car.
I know, but-
tea is hot, right?
For big
So
cars.
if you put the ice in the tea,
Maybe it is for
the tea will cool down, right?
Even old stuff.
So,
Like you always hear
So it's
voices
from hot to cold?
in the engine.
so it's from cold to hot. The ice is cold. Look, the tea is hot.
Yeah.
You put the ice in the tea becomes cold.
Yeah, so it's hot to cold.
Here,
the tea,
أيوة بس don't, okay, leave it. Don't worry about it. If you are eating food, the food is hot, so you blow
And
it.
then there are different types of pressure.
Yeah, hot to cold.
Yeah.
That can
No, it's
harm
not.
your car, like,
It is!
Yeah,
Look, bro.
The food,
No,
the
there are
food
the
from
leaded,
hot and it
leaded
becomes cold.
Yeah.
Yes.
Yeah.
French is a good example.
You have nice
When you put hot food
we have
into
nice
a
one
French,
five.
it cools down.
Yeah, so hot to cold.
There's the one.
No, but the French itself, it doesn't lose the heat.
But the food
or
is
gain.
from hot to cold.
Yes.
No, look, it's not hot to cold. You're comparing two things. So hot to equal to cold.
No, she's correct. The food from hot it becomes cold.
Yeah.
But the flow,
But
the flow of heat.
Yeah.
No, wait, sorry. The temperature of the food decreases. The temperature,
Yeah.
the kinetic energy of the
Yeah.
food decreases.
Yeah.
But the flow of heat is from cold, from the fridge, which is cold,
Yes.
to the food, which was hot. So temperature and heat, two different things.
Yeah, when the second law is not about the temperature, it's about the movement of the heat.
It's not the way you're thinking of it. Like, it's not something that's losing heat to something else.
Well, it's not the heat, but it's about heat and hot are two different things.
Yeah.
Okay? Heat
Why is the building
is
called
energy,
building?
hot is temperature.
What?
Why is the building called building when it's already built?
Why?
I'm asking why.
Do you know the answer? Okay. It's supposed to be a joke in the front, so
Continue.
Did you get it? Or are you still confused? You're confusing me. I don't get it. Okay. I'll try this again. Look. The tea is hot. Right? And then you put the ice in the tea.
The bird.
Okay?
Yeah.
So
I might say.
the cold temperature from the ice
They know that it has to be.
is moving to the hot tea and making the tea cold.
Oh, really?
Yeah. Duh.
So the transfer is from cold to hot.
Yeah, but it's a temperature.
So it means you see the ice, not the tea. Like,
See the ice, but not the tea.
No.
like,
So could you put it in temperature?
The ice melts.
Cool.
but
Because it's losing energy
Yeah,
through
show me
I don't think that's a good example.
Just show.
I don't think that's
the,
it.
the coffee can lose energy from hot to ice.
surroundings.
Ah,
I don't know. Yeah, I'm confused too.
Yeah.
Okay.
Yeah, 2 weeks.
what's the question?
We're trying to explain to her the thing. And now we're confused.
You know what? Can you go back now with you in public?
Why are you thinking about the next 60 years?
I don't think my life has been alive.
I feel like there are some.
Yeah, there should be.
Why do you think so much?
One, you're toxic.
Yes.
Maybe in the desert.
He just told you something. Go with
Report,
it.
report.
In the forest.
No, in Germany, like they have a lot of parks.
Even in
Some of
forests,
them,
I don't
yeah.
think they're public, so I think it's fine to public.
So I'm not sure.
Yeah.
Like usually what people
It
barbecue,
depends, not
they
all
do
about
the tone.
Not all. That's all the food.
Oh, so you need a.
The way they do it in the
Units?
Yeah.
Solar energy is units.
They have
Same thing.
Joule?
Yeah,
energy.
They're all energy, so they're all joules.
But he have a
What about this?
All, they're all the same.
All the same?
Yes.
Yeah, they're all
You know,
energy.
actually,
Yeah, but they're not around that thing.
how do you
Because it's made of
This is the pencil?
Yeah.
Okay. Couple. No.
Okay.
This is the fire. Fire is
Oh,
what?
okay.
Okay. This is phone.
Yeah?
No, phone.
Okay.
Okay.
Hang. This is hang. Hang like that. Okay.
Okay, happy?
Yeah, okay.
Okay, so the heat. This is hot. You are in high temperature.
I use
Okay.
radio.
The heat transfer is from hot to cold.
What's W?
This is the normal.
Energy.
This is happening to work. Heat goes from hot to cold. Always.
Yeah.
Unless you force it to go the other way.
W is
No.
going down.
Yes, listen, this is the second one. I'm not making this is one certain.
But I also can this.
No, gravity doesn't pull you downward.
What?
I also can make it become cold.
You make it. If you make it, yes, that's right. But if you don't do anything, it will go from hot to cold.
Yeah.
Oh, and that is-
What's the acceleration due to gravity?
Huh?
What's the acceleration due to gravity? The number.
Gravity?
Yeah. What's the number?
Natural.
No! No! Well, fuck yeah!
No.
But like,
What the fuck?
but like, it can be like the weather. It can be maybe.
What?
No,
Yeah.
Okay. Okay, good. If you don't do anything, it will go from hot to cold. But if you do something, you blow on it, or you put ice, then it's gone from cold to hot. Yeah, okay? Okay?
But
But fuck, what?
But what?
if this small
No, of
fire,
course.
Yeah.
Then how do you say
it
that?
can be.
Yes, it's a small fire, then very small fire.
Okay, but if this is not fire,
I don't know why.
if
I don't know, but
this
it
is
is.
ice.
Then it's different.
No, it's a
No,
melting
shut up.
and it becomes
Listen, come here.
This is it.
I don't know.
Listen.
Your engine works better with the.
Ice, what's the temperature of ice? Zero.
No.
What's the temperature of you?
20, no, 37. No, 37, yeah. No, 36.5.
Okay, 37. Today you're feeling warm. Which one is hot and which one is cold? Hot
Yeah.
and cold. If you put the ice in your hand, the ice will melt or you will freeze.
I will be cold in my hand.
The ice will melt, yes or no?
Yeah.
Okay, so the ice. So
But
the
my hand is cold.
Shut up. Listen, the heat transfer is from you, the hot, to the ice.
Or maybe because
So the ice will melt.
Okay.
So it's from hot to cold.
Yeah.
Just like this one, hot to
But what
cold.
about my hand?
Yes, but your hand.
It will be cold.
Yes. No. This is what we are
You
saying.
only have one hole and a hand.
Your hand will become cold because the ice
He was saying.
is applying energy on it. We don't know what is that, but it's applying energy on it. We put you in the fire, you will burn because it goes from hot to cold. If you put the ice on your hand, the ice will melt because it's going from hot to cold.
But the fire and the ice is different. I mean, like the fire
Lee,
makes
send me the
the ice just a little bit,
Listen.
but it's the huge ice.
It will still melt.
Yeah, the part.
No.
It will still melt.
No.
Yes.
Because of the weather, not because of me.
No, not because, of course because of not of you. Because the surroundings is more hot than the ice. So,
But what happens is like
listen, shut up and listen. This is this big huge ice. Okay? So this is the cold. Okay?
Yeah.
The air around it. Is it cold or is it hot?
But if
Okay,
in where is it? The
Antarctica.
penguin,
Where the penguin lives.
North Pole.
yeah.
Yes, North
South,
Pole or
South,
South
South,
Pole,
South.
whatever fucking pole. Stepping pole. If you go there,
Mm-hmm.
what's the temperature of the air?
Maybe minus.
Is it more than the ice or less than the ice?
That's
If you answer this wrong, I will take my shoe and put it in your
Less
mouth.
Alright.
than the-
Less than the
Alright.
So what will happen? So the surroundings.
But it's okay.
Shut up.
I don't know.
The surroundings is hot
Isn't massive?
Yes,
and the ice is cold, right?
What's up?
It's hotter than the ice. The air around it.
But.
No.
Oh, sorry.
What?
No? Okay, you say no? You say they're equal?
No.
You say they're equal?
It's like
Okay, then if they're equal,
They are good.
that's the first one. There is no change. This will stay cold, this will stay the same cold,
But
the
and
same
then I'm
temperature.
in here.
Okay, then you will be hotter than the ice, right? Because you're 37, 36.5.
Yeah.
Okay, this is wrong.
Oh my God, please.
This is wrong.
Yeah.
36.5. Who is the hot and who is the cold?
I'm hot.
Autistic and
Okay. And the surroundings is the cold.
Yeah.
Okay, who will be...
That's another T-shirt I want. Who's the hot and who's the cold? So many great T-shirts.
I am the warm.
Okay. Hey, I have the results, but first things first, I want to get through the answers to
Rest
this.
in peace, Uncle Fair. Fair. You're the only fellow that I ever knew. I guess you every better you. Prophecies that are made way back in the veil.
Word. All right.
We'll finish this later.
That's right.
This isn't over. Right.
She doesn't want to understand, he just wants to argue. That's what she wants.
That sounds like a student
I'm not this bad.
Maybe you know how I feel now.
Stephen!
Okay. Did you get an answer for the first one?
Yeah, I got something, but I don't know what to do.
Well, let's see. Let's see. So, what's the formula here? Delta U equals,
Q minus W.
and here, what is the Q? 20,000. And what's the W?
Work it out.
We have to work it out, Joe.
Yeah.
It's the kinetic energy. A half m
Yeah, it's 5,000 only.
v squared.
Yeah. V is 1.
Somebody use MGH. How many trains travel vertically?
MG. Wait.
Right, that's worse. 20,000 minus 5,000, 15,000, so 15 kilojoules. Okay, is that okay? Right, that's number one. Now number two. Coal is burnt with energy Q released, and this produces work W, and there's an increase of delta U in the engine. What is the efficiency? So, what's the formula? Yeah?
Is it 50%?
No. Definitely not. What is the efficiency formula? It's the useful work out over total work or power times 100. Now, what is the work out here? Well, this is the W. What is the work in? This is the Q. That's what you put in, and W is what you get out. Okay. We have a formula, though, that says Q equals, what's it? Delta U plus W. for that one? Times 100. Yes? Okay. Yes. So, what I want you to see here, I suppose I could simplify this a little bit. I think I will.
1 over u, delta u plus
1 over, yeah, like divide everything by w, yeah. So this is 1 over
1,
delta u over
no.
w plus 1. Is this the amount? Anyways, I don't have to simplify it. I'm happy to leave it like this. This is the key point I want here. Unless I say I want it a particular way. No. Okay, so this is the... You could leave it like this or like this, but this is the key way I want it. Although this is okay too. The reason I want it left like this is because I hope you can see that this must be less than 100.
Yeah.
Must be, because the bottom must be bigger than the top. How much bigger is the bottom than the top? Well, in this case, by delta U amount.
Yeah.
Another way to state, earlier I said second law states that heat cannot flow from cold to hot. It must flow from hot to cold. Another way to state the second law is like this. Delta U is not 0. That's another way to state the second law. Now, if you state the second law that way and use this formula here, it means that it's impossible to get 100. Why is it impossible? Well, because this must be bigger than W, because this is not 0. So, if you state the second law this way, then another way to state is that efficiency must be less than 100%. So there's actually a few ways to state the second law. The first way was the simplest. Another way to state it is that delta U is not 0. And a third way to state the second law is efficiency must be less than 100%. This means that this is impossible. You can't have 100% efficiency. It's impossible. It's never going to happen. Never going to happen. And this is actually one of the laws. And certainly, if you cannot have 100%, you definitely cannot have this.
Yeah.
Except in one situation. Yes.
Which is?
After you study maths and physics for 4 years and do a master's in it, I'll tell you. But you're not ready for it. If you can have it greater than 100%, then what you've done is you've made free energy, because you got more out than you put in. There are many people online who claim that they've been able to do this, but there is only one experiment that I know of that actually has done this.
Which is?
Oh no, like I said,
What is the name of the science?
you're just not ready for it. No, you're just not ready for it. I'm sorry.
Isn't it a sad thing that you can't get 100% efficiency?
No, I was thinking if you change the material.
A sad thing? I wouldn't say sad. It's an annoying thing. Because it means that no matter how good your engine is, it'll never be 100% efficient. Which, is annoying, because it means that the best you can hope for is like 99.9 or something. You can never get 100.
I was thinking,
Yes.
if we make an engine with, let's say, a material that we keep cooling it down or never heats up.
But how would you cool it down? You would have to use something like air conditioning.
So the Q will be bigger, won't it?
Yes.
Yeah, so it still won't.
Yeah. So I'm sorry, it's not going to happen. Let's have a look at results. Okay, so you can come up one by one in order on the list. So the first person is Fuang. You want your maths results?
0.
Yes, she got 0%.
Huh?
Come on. Don't listen to him. Yeah.
Do you want us to go and see, or should I just say it?
Can you just say?
A star.
But the
85. Okay. Andrew, C or state? You can see. No. No, I mean, I shouldn't have forced you to feel like you have to have me say it out loud, because that would be unfair to you. Not that it's bad. Look how sad he is. Right. That's you. Yeah. Yahya?
Yeah, I know.
You do? Oh yeah.
I had to.
Faisal? Oh yeah. David? You want to come up? I want to say it. Lee, sorry. It's still David on this.
Is it the same as mine, or is it lower?
Not bad.
Not the same.
Omar, you want to come up or see?
What's the highest?
Right up.
99%?
This one here. Mm-hmm. All right.
Yeah, but he
What?
got 98.
Oh, you know it.
Yeah, 98, yeah?
Yusuf?
Yeah.
Want me to say it or is it
Yes.
17? Oh, sorry, no, 7.
What?
97. Okay.
Really? 97? You sure?
I'll double check it. These are only my first attempt at marking it. I'll double check everything.
No, that's fine.
I have to.
We believe in you.
No, I know you do, but Manchester require me to mark it twice. So maybe the second time around I'm like, oh no, why did I give him a mark here? Oh, no. Although I don't think it will drop a grade.
Are you happy with that?
Oh wait, you're gonna remark them, and that means there's a chance of you finding a mistake.
But there's also a chance that I found a mistake I made and then required to give you a mark. It goes both ways. Now I'm not double checking for you. I'm also double checking for me that I marked it right the first time. You know.
They come up at 9.
You give me a B for predicted mark. Guess what? 1 mark away from 100%. Okay, I wanted to
I
ask
stand by that B. Because it was a very easy test.
Question.
Yeah.
Now, how would they be added to the 10% in the final grade?
A tenth of this.
So 99.9?
Yeah.
So it doesn't make 100? So it does.
It does not make 100.
It makes a 10, I mean.
No, it doesn't make a 10. It stays at 9.9.
Really? They count
So
the
they
one?
that's 0.1%? Why don't they just round it up?
The final mark is rounded up, but not the components. So if your final mark was 90.9, it becomes 91, but only at the very end, not the individual component. So this will add 9.9 to your total.
Okay, yeah. If the final is rounded, then that's fair, yeah.
Yes. And not only is it rounded, it's always rounded up.
Oh.
So a 69.1 becomes 70. Half a mark for free. Yeah. So technically you only have to hit 69.1 to get an A, technically.
Another A star, and their faces.
Yes, but not today. Yeah. I don't know. I know. And it's difficult to believe that he got more than you. No. Just because he's here, you don't have to be polite. I know. You're thinking, you're looking at him, how did he do better than me? I think his English is better.
No!
No, get over this.
Yeah, don't make
All of you.
Oh yeah, maybe. Definition, I almost.
Don't
Yeah,
care.
yeah,
Don't care.
yeah, it's his English, yeah.
You can keep the rest of it.
Nice.
We're finished?
We are